All right. Minimize this. Feel free to send me your questions on the chat in case you had any. They will not appear obviously in the screen recording, but hopefully it will. I'll get the notifications directly on my phone, so or the other desktop. We'll see. Okay, so let's talk about. Last time we have talked about the. Last time we talked about graph theory, how you would represent graphs in memory, and general techniques of retrieving stuff from memory, like when you would like to play with graphs. And right now, what we need to do is we need to have the ability to ask the graph questions, right? Investigate things. So if we presented a problem in a graph, you would like to know, for example, like how can you find the shortest path, for example, or are these graphs connected? For example, like if I've actually given you something like this, like in the computer, and obviously, I mean, because I drawn it, it's obvious for you that you can see it. But let's say you would like to ask the question, like if somebody giving you a data structure, for example, a adjacency matrix of nodes, and then you would like to ask the question, okay, is this graph fully connected or not, right? Right now, these questions can be answered through applying certain algorithms. One of the famous algorithms, which we're going to look at right now, is DFS and BFS. And in DFS, usually we use it in order to know whether, for example, right now, let's say it's actually, we use it like a helper method in order for us to know what are the connected components, what are the connected graph, like what is exactly connected and what is not connected, for example, right? So this is the job of DFS, for example. In BFS, in BFS actually it's used for pathfinding, for example. Like if you have a maze and you would like to go through pathfinding, you would like to find a path from one point to another in a maze. BFS is one of the good algorithms. There are many better, but it's another. We're gonna talk about this probably a little bit later. But in any way, I just wanted to just give quick introduction about this. So DFS, which stands for depth first search. Okay, and it is a generalization of a pre-order traversal. And we're going to talk about what a pre-order traversal in a minute is. Pre-order traversal. Okay. So practically speaking, we process vertices. So we first process I'll need to probably rewrite this a little bit better. Vertices. Adjacent. So for example, like we first process vertex V, for example. Let it be like this. Vertex V. Then traverse all adjacent vertices to V, to that V which you have explored, okay? So practically speaking, you are not allowed to go elsewhere unless you grab the vertex and then, for example, you grab a vertex and then you have multiple vertices and then you have more vertices. So you grab one, you actually visit it, and then you go there and you visit it, and then you go there and you visit it, right? So you are not allowed to go anywhere else unless you are done with the whole vertex, like with the whole in-depth search, let's say. So that's why it's called depth first search. It doesn't care about visiting everybody else. It doesn't say, give me all the children. It just gives me the first child and then give me the next first child and then give me the next first child. This is how it actually like behaves. Let's say so. Okay. Like in a very layman terms, I would say. So there are certain terminologies which you need to know about. Terminologies. The first thing is that you need to understand what a visiting means. So visiting a vertex means you just reached a particular vertex. Okay, in a graph, obviously. So you have reached there, you don't do anything. You can think of it like, for example, highlighted. Okay, like as if you highlighted, like you marked it. Okay, and that's it. This is what visiting means. You just arrived there and you didn't do anything else. Exploring, that's another one. So exploring a vertex means you visit or you visited. Actually, exploring means they are in the thing, but so you visit all adjacent vertices of a specific vertex. Okay, you are highlighting. Okay, so for example, let's say you are having a graph like something like this. Okay, so here I visited a node or I visited a vertex, and then I start to explore. So exploring means I have to visit this guy and this guy. Once I visited these two guys, highlighted, this guy has been fully explored. Okay. However, these guys has been only visited because I haven't explored all of its children, and it happened to be that they have only one child. So if I visit this guy, and this guy is fully explored. This guy is still visited. So if I explore, or if I actually visit this guy has been already explored fully because there are no other children, so fully explored. And this guy doesn't have any other children, fully explored. Okay? Does this make any sense? In terms of terminology, I mean.
Yes.
Okay. So this is very important to understand, like the difference between exploration and visiting, because usually like we rely on this in terms when we are working with the algorithms in general. Okay, so basically speaking, how DFS works, in DFS, when we reach a dead end, we backtrack to revisit other unexplored vertices. We backtrack and revisit Can you hear me now?
Yep.
Okay. Yeah, internet problems and Wi-Fi issues. Let's see. Screen recording. I hope that this recording's still on. Let's see. Is recording still on? Perfect. Okay. All right. So, carry on, yes? So what I've said, hopefully before The internet went out. So in DFS, when we reach a dead end, we backtrack and revisit other unexplored vertices. This is basically what DFS is all about. So let's see how DFS works really quick. So assuming that you are having the following. So one, write it a little bit bigger. 1, 2, 3. It has like 6, 7, 4, 5. Okay, and I ask that you create a DFS starting from a certain vertex, because you have to name what is your starting point. So let's say I'm gonna pick up 1. Okay, so with 1, I just simply I will just simply say, okay, 1. So what are the adjacent vertices? You have like 2, 4, and 5. So 2, 4, and 5, I could actually pick up 2, for example. So I'll have like 2. Then I can say, okay, give me one of the children of 2. You see, I'm ignoring this, I'm ignoring this because it's depth first, for example. Okay, I didn't actually say give me 2, then 4, then 5. I just simply said give me 2 and then give me one of the children. Okay, and then I just simply say, okay, give me 3. So I'm just going to put 3. Now 3 is fully explored because there are no children. So I'm done with 3. So I will go back here and I say, okay, are there any children in here? So there are actually. So there's 6. So I can pick up 6. 6 doesn't have any children, so we can say it's fully explored. So we get back to 2. 2 still have 1 child, which is 7. Then we say that 2 is fully explored, so we go backtrack to 1, and 1 still have a couple of children which haven't been explored. So right now we have 4, and then 5. Okay, so this is one of the potential solutions to a DFS in this case, for example, for this particular graph. Okay, it is very like, how can I put this? Like, it's very straightforward. There's nothing fancy about this. If you would like to do, if you would like to look at it from a tree perspective, if you look at it like, so for example, if so a DFS is a pre-order traversal. So if I actually give you a bunch of nodes like this, so if I give you a binary tree, six, 7, okay? If I give you a binary tree like this, and then I ask you actually to traverse this, what you will do, you will go actually in depth all the time until you reach here. So for example, your DFS will be 1, then 2, then 4, right? But then you have to backtrack, and then you see, is this guy's fully explored? It isn't, because 5 hasn't been visited yet. So I'm gonna have 5. Now this guy is actually fully explored. We backtrack again, and then we go downwards. So we have 3, then we pick up 6, then we pick up 7, right? You backtrack, and then you pick up 7. So this is basically what would be your DFS traversal on a binary tree would look like. Okay. So let's assume for a minute that we pick up another example. So how would you actually solve something like similar to this, for example? So, and there are many ways of solving this, by the way, but I'm gonna use one. Let's say something like this, for instance. And then we say, okay, we need a DFS for this guy. Now DFS for hang on. Now a DFS for this guy, usually you would use something like a stack. Okay. So what would you do in this case? Let's say that the starting vertex is 1 and you are using a stack. Okay, so this is the starting point. So assuming, or it's like given. So in the exam, you would say, I will give you a graph, and then I say, find me a DFS starting from that vertex. And then you're going to have to list all the vertices correctly in a directed or undirected graph. It depends. So, but in a directed graph, it's even easier because you have a direction. In undirected graph, you tend to have multiple solutions per graph. But in any case, yeah, so assuming starting point or starting vertex, let it be starting vertex is equals to 1. So this is the like number 1. So what would you do is you push this into a stack. Okay. And then, as we already have said, that you need to pick the next vertex you need to explore, because again, you need always to go in depth. You don't need to explore all the children. You explore only one. You pick up one and you go with it. So for example, I could pick up 2, for instance. So I'm gonna push in 2. Okay. Coming up next. So for example, right now, I will ask does 2 has any children? It has, right? Now you have multiple possibilities. You could go for 7, you could go for 8, you could go for 3, right? So I can actually say, aha, okay, there is still more children to grab. So I'm gonna grab, for example, 3. Okay, for example. And then 3 still have children. So I cannot stop yet, right? Because 3 can be actually having 4, I can go from 3 to 4, I can go from 3 to 10, and I can go from 3 to 9, right? Let us actually make it more fun. I will actually pick up 4, right? So we push it here. Now here's the interesting part. From 4, 1 is already visited, right? 3 is already, I'm coming from 3, so 3 is already visited. So I can say that 4 doesn't have any more unexplored children. So I will pop it off the stack. Okay. So practically speaking, my traversal so far was 1, 2, 3, 4, right? My traversal so far in the stack. However, I'm going to pop 4 off the stack so I can backtrack, right? So I have right now going to 3, isn't it? So I'm looking at 3. Let's see. What else wasn't explored? We have 9 and we have 10. So let's actually pick up 9. So I'm going to push 9 to the stack. So 4 doesn't exist anymore. I'm going to push 9 to the stack. Okay. Now here's 9, obviously. Now 9 doesn't have any children, and I can only reach 3 here. So 3 is actually fully, like not 3 fully explored, but 9 is fully explored. So I can actually pop 9 off the stack, right? And we are back to 3. So the question here is, what else is left? So 4 is fully explored. like 4 is already has been visited, 2 is already has been visited, 9 has been visited, only 10 is left. So I'm going to push 10 to the stack. Now 10 is fully explored. There is nothing else connected to it other than 3, which I'm coming from there. So I can actually pop 10 off the stack. 3 is fully explored right now because I have visited 2, I have visited 4, I have visited all these guys or fully explored everybody else. So I can pop 3 off the stack. Now we are back to 2. Now, does 2 have any other children which we haven't explored? So yes, we have not explored 8, 7, or 5, right? So you have like 3 roads or 3 points you can actually connect to. So for fun, I'm going to actually pick up 5, for example. So I'm going to push 5 to the stack. Now 5 does have a child, so it has 6. So I'm going to push 6 into the stack, right? Because there is nobody else to choose from. Now 6 doesn't have any children, and I'm coming from 5. So right now 6 is fully explored, so I pop it off the stack. Now 5 has been completely, or maybe not fully explored because there's still connected to 7 here. So I'm going to push 7 to the stack, right? Now, from 7, we have multiple options. 2 is already have been visited. 5 has been already visited. 8 hasn't been visited yet, so I'm going to push it to the stack. Now, what will happen here is you're going to see that 8 has already been visited, like it's already like connected to 2, which has been visited. 7, I'm already coming from there, which has been visited. 5 has been visited, so I will pop this off the stack. So this is done. Backtracking to 7. Does 7 have any other children? So if you look at this, 2 is already there, already have been coming from there, 5 coming from there. So we pop 7 off the stack. You look at 5. 5 has been already explored, coming 2 and 7 and 8, so we pop it off the stack. 2 has been already fully explored, so we're going to actually pop 2 from the stack. And then when you look at 1, is already has been fully explored, so we pop 1 from the stack. So we have traversed using DFS the full graph. Okay. Could I have gone, for example, 1, 4, 3 instead of 1, 2, 3? Yes, because this is undirected graph. Okay. You can go in whichever way possible. So there might be multiple solutions to this, given like a starting vertex. Could have you gone from 2 instead of like going to 5 and then 6 and then 7 and then 8? I could have went 2, then 8, then 7 and 5. Yes, possible. It's undirected graph. Okay. So that's how you would, for example, approach DFS like on pen and paper basis. So one of the notes which is important to tell here, we do not, and if you already hopefully have noticed, you do not explore vertices that has been visited. So if I visited a vertex, I don't explore it. I just simply ignore it, right? Because later on, we're going to explore it completely when we pop it off the stack or when we get it from the stack. This is actually DFS, nothing more. Do you have any questions about this? Anyone? Do I have audio? Yeah, I do. You guys can hear me? Hello?
Yes, we can.
hear you.
Yes, yes.
Okay. Okay, please be faster because I have no other feedback other than audio right now. Okay. All right, so if there are no questions, we can go to BFS really quick. As you can see here, it's super simple. There's nothing fancy about this. So breadth first search BFS. Breadth first search is another traversal algorithm to traverse a graph. Like how can you explore a graph? So it is the same as DFS, except that you just simply like explore all the children, like you visit all the children before you actually moving on with the hang on. So to say it better, you explore every vertex you stand on, meaning that you visit all the children and then you move on to the next vertex so you can visit all the other children. Okay. So that's the basic idea. In depth first search, we don't visit all the children. We pick up one and then we keep sticking with it. And if it has a child, we pick up the first child we see and then we move on with it. With breadth first search, you cannot move to explore any other vertex unless you have visited all the other children, and that's it. Okay, so it is actually it is also one of the famous applications for it. So it is very useful in finding shortest path in unweighted graph, which is very important. So if you would like to have, if you have a maze, right? So if you have some sort of a maze, which I don't know how to draw mazes, but you get the idea. And you would like to traverse that maze somehow. So let's say you have the exit right here. Okay, so this is your exit. This is your starting point. And let's lock this so we can actually find something, hopefully. So yeah, so if you would like to find the path to the exit, right, it is actually very good at it. And not only that, but it has to be unweighted, means that there are no costs when you are traversing the graph, because if you are looking at a maze like this, a maze is in fact a bunch of cells. It's just a very dense graph, nothing more. Okay? And what happens is that you have walkable and non-walkable nodes. So these are the ones which you can go through, these are the ones which you cannot go through. And then suddenly you got yourself an interesting graph. Everything is connected, obviously. Okay? And then you have to right now traverse traverse the actual maze. In fact, like you could actually think of the maze like because some people actually cannot imagine it very well. So let's say here's the grid which we are working with. And you would like to say, okay, can you please navigate me through a maze that has, for example, the exit here? What you would do is you would say, okay, what are my walkable nodes? So you can say, okay, these are walkables. These are walkables, right? But then you will ignore in your graph any non-walkable node, okay? I don't know how to construct a maze in real time, to be honest, but you get the idea, hopefully. Okay, so let's say this is not walkable. I'm building walls right now. So let's say you have a wall that looks like this. Let me erase those two guys. Okay. So let's say you are starting from here and you would like to end right here and you would like to find your way around. What you will do is that you're going to construct a graph that looks like this. Your graph in memory, or when I draw a graph, it will look like this. The fun part is you have just one more check to do whether this is the vertex you are searching for or not. And you have to push into another stack or another queue, let's say. Where is what was the previous node you came from before you reach to this point, and that's it. And in fact, this kind of graph, which is similar to this graph, by the way, I mean, you think about it, it's like something similar to this. It's just a little bit more nodes into it. And if you pass a BFS through this thing, it will actually traverse the whole maze and find you a shortest path to it. But again, there are more optimal algorithms than this when it comes to known terrains or known areas. Okay, so if you have a map that is known, so if your maze is known, like somebody give you the maze as an input, there are better algorithms and faster algorithms than BFS. If you are doing robotics, for example, and you are trying to explore areas that are unknown, so you need to make a map and then you make the shortest path and stuff like that, BFS will start to show its promise, besides other algorithms, which I will not mention here right now, but yeah. I'm just trying to, like give you the reasoning behind like what would you do with a BFS in general. So let's say, so for example, to get back to the exams, hacking and stuff like that. So if we have a graph that looks like this, 3, then you have from 2, we get the same example like 6, 7. Then we have here 4, then 5. Okay. And then I ask you to start giving a BFS starting from vertex 1. Okay. What you would do is that say, okay, give me 1, then you explore everybody else. So like you say, I visit everybody else. So you visit 2, then 4, then 5, for example. Okay. Then you stop. Then 1 is fully explored. Then you say, okay, I'm going to pick up 5. Is 5 is fully explored? Yes. 4 is fully explored? Yes. 2, is it fully explored? No. Then we visit all of his children. So we say 3, 6, and 7. Now 2 is actually fully explored. You are actually done. This is BFS. So you take a node, you explore all of its children first, or sorry, you visit all of its children. Then once you are visiting all the children, you are done exploration, you pick up the next child, and then you ask what else is not explored. Okay. Could I have actually picked up, like 2, then 4, like exploring 2, for example, once I'm done with 1, 2, 4, 5, or 1, 5, 4, 2, yes, I can pick up 1, 5, 4, 2, and then pick up 5, then pick up 4, then pick up 2. I could have done the same. It's also a valid solution. If you look at BFS on a binary tree, though, it's actually quite interesting. So if I have 1, 2, 3, 4, 5, 6, 7. BFS in binary trees, sometimes they also call it has a level order traversal, meaning that you visit based on levels. As I already have said, in BFS, you need to explore like every level you are going, like you have to visit all the children of a specific node you are exploring. So for example, if I say 1, then you're going to pick up 2 and 3. Then you pick up 4, 5. Then because 3 has been visited, then you pick up 6 and 7. Okay, so you go this way. Practically speaking, it's just level order traversal. Okay, this is what a BFS is about. So if you look at BFS using the similar example like this one, which honestly, let's see, can I actually copy this? Let's see if I have the ability to copy. Yes, please. Let's see. And can I? Hang on. Come on, give me a keyboard. Oh, paste. There we go. Perfect. So, given something like this, with BFS, usually we use a queue, for example, in this case. So let's say that you have a starting point. Oh, let's say you have a starting point, which is 1. Okay, so assuming starting vertex equals to 1, so which is this one. So I'm going to push into the queue this one. Okay. So what would I actually enqueue? So what you will enqueue is going to be, let's say, 4 and 2. So you're going to push in 4. You're going to push in 2. Okay. And then you actually have fully explored 1, right? So 1 is done. So actually you remove it from the queue. You don't look at it anymore. Then you look at 4. So actually let me write here. So BFS is going to be 1, 4, and 2. Okay. So we grab 4. And then you say, okay, what are the possible children we have here? We have 3. So we're going to push into the queue 3. And you push it 3. Okay. And then you say, aha, okay, so 4 is actually fully explored. Right now, we remove it from the queue. We pick up 2. So 2 has been so 2 actually has 3, which has been there. We have still 8, 5, and 7. You can actually pick up whatever order you like, because this is undirected graph. So for example, I will go this way. So I'm gonna 5, 7, 8, 5, 7, 8. Okay. I keep forgetting actually, like to push these guys. So hang on, 3, 5, 7, and 8. Okay, I'm just traversing the graph, nothing more. Then you say, okay, so 2 is actually has been fully explored, so we move it from the queue. So let's see what is next. So 3. So 3 right now is not fully explored because we need to explore all of the children. So we have 10 and 9. So we have 10 and 9. Okay. 3 has been fully explored. You remove it from the queue. Look at 5. 5 has 6. Is 6 has been explored yet? Nope. We put it in. All right. Also, we have to push. We should have pushed 10 and 9, by the way. I just forgot. So yeah, so we should have pushed 10 and 9, but I didn't push them because they were the end nodes. But obviously we're going to remove them later. So 6 is here. So 5 has been fully explored. We remove it from the queue. 7. 5 has been explored, has been visited. 8 has been visited. So 7 removed from the queue. 8. visited, so it's connected to 2, connected to 5, connected to 7. It's already have been visited, like fully explored already, so we remove it from the queue. 10 doesn't have any children, remove. 9 doesn't have any children, remove. 6 doesn't have any children, remove. We actually have a BFS. Done. So we actually traversed the full graph using BFS. Okay, so this is, practically speaking, a BFS on an undirected graph. On a directed graph is much easier because you don't have, like, if you have something like this, for example, right now number 1 has only one choice to go to, which is 2, right? It doesn't have multiple choices anymore. So this is like with directed graph it's easier, but with undirected graph it's a little bit more tricky. Like you need to pick one, like you can actually, no, I wouldn't say it's tricky. It's like based on whatever it actually comes out in your data structure, right? Like how you input the data and which data comes up first. So yeah, that's pretty much it, I guess, for DFS, or sorry, for BFS and DFS. Do you guys have any questions for this one? Anyone? Okay.
No questions.
All right. If all good, I will actually give you a 10-minute break, and then we move on with binary search trees, and then we can conclude today's lesson. So see you in 10 minutes.
Okay.
right. I think 10 minutes has passed. I don't know. I cannot recall, honestly. I didn't look at the wall clock when I mentioned the 10 minutes, but hey, we can actually get started. So binary search trees. Or BST for short. Okay. First of all, it's very important, like to define them correctly, because their properties, their properties are important to the success of its purpose. Like, well, I would say success of its purpose, but like it's important for its purpose. That's very that's very important here. Okay, so so what a binary search tree are by definition, they are acyclic. If it really stops glitching, I would be very happy. It's acyclic, connected. Undirected graph. And a little bit of space there. This is what a binary search tree in general, or binary trees in general, are. It's a connected graph with n nodes, n number of nodes, let it be like so. Okay. And n minus 1 edges. Okay. So if you have 10 nodes, that means that you have 9 edges in that binary search tree. And any two vertices are connected by exactly one edge, which is very important. Okay. So only one edge. You cannot have something like this. This cannot happen, or rather like this. Okay. This is not a binary tree anymore. This is more like a graph, like a regular graph right now. So in a binary tree, or a binary search tree rather, it is you are always having this kind of format. Okay. It's rooted, so it has a root. Okay. And sometimes if you look in books, usually people represent binary trees like this. Then sometimes, let's say, you have a huge tree right here. Okay, but they are concerned for some reason, they are explaining some stuff, or you are talking about something that is important to you in this side of the story, not this side. So what they usually do, they substitute this with something like this, with a triangle. That means that there is another piece of this graph that is actually big, but I don't care about it that much, but I care about this issue. So I'm actually representing it more in detail. Here I'm ignoring it. So I'm just simply putting 1 and a triangle. Maybe something like this, for example. There you go. Okay, it could happen to see, you could see this in books. Okay, so it's just a notation, nothing more. Okay, that you are saying that this guy, so sometimes we use a triangle as a notation to substitute large or relatively large part of the graph or the binary tree or the BST, whatever, or the binary tree is usually like, it's quite common in binary trees in general. Okay, so that's what I wanted to like mention because you could see it actually in the books. We already have seen, like we already have talked about back when we were, talking about the heap, if you remember. We talked about the complete binary tree, not complete binary trees. So, for example, this is a complete binary tree. Okay, this is not a complete binary tree, if you remember. So, not complete. Okay. Really, Microsoft need to get themselves together, honestly. Like screen sharing with MS Teams breaks like, yeah. Anyway, so this is a complete binary tree. This is not a complete binary tree, and this happens to be like this because we said that we shouldn't have any gaps in the array, if you remember, right? So when you represent an array, so you represent this guy, then this guy, this guy has nothing. So you're gonna have actual like empty elements in the array. We talked about this already. So this is not a complete binary tree. So it has to be in a binary search tree. We need it to be a complete, I wouldn't say we need to be complete because when we insert stuff, you will see it's gonna be not complete. But generally speaking, we talked about these types. I'm just reminding you again because you're gonna see these shapes. The height of a binary tree, the height is always log n, if you remember, okay? Because if you have something like this, so you have 1, 2, 3, and you have here 8 elements, or how many? Sorry. 1, 2, 3, 4, 5, 6, or 7, or how many? 1, 2, 3, 4, 5, 6, 7. So you have 7. Okay. Well, I'm missing something. But in any way, I mean, it's always log n. So this is like the height of the binary tree. Okay. Now there are a couple of things about the binary search tree that you need to know about. First of all, how do you insert in a binary search tree? Why we call it a binary? Why are we interested in this? because you might actually would like to organize your data in a tree structure, and you would like to keep finding any node in the tree structure in the log n rel, let's say. Okay. So binary search trees are a special kind of a binary tree. So our binary trees where elements are sorted okay. Where elements are sorted, where the parent is larger than the child node. Okay, or you could actually reverse it. A parent could be smaller. Oh my God. Than a child node. Okay, so you could have like ascending or descending order of sorting. Okay, so depending, let me write this down so nobody gets confused, depending on the sorting order. Okay, you may or, oh my goodness, or may not allow duplicate elements usually we don't. Usually we like to keep things unique because it's easier to find and stuff. But usually we don't allow duplicate elements. Okay. So if you are, for example, trying to insert something like, for example, like you could actually have something like this. So 4, 4, and 5, this could happen, even though we wouldn't, I mean, not recommended very much. But for example, you could have a binary search tree that looks like this: 4, 7, then 3, then 6, then 8. This one is the opposite, right? So this one is small, and everybody else in the children, on the right-hand side, it's bigger. On the left-hand side, it's smaller. I should have actually probably mentioned this. Hang on. So BSTs are binary trees where elements are sorted where parent is larger than the child node. Actually larger than the left, let it be like this, than the left child node. And let it be and, because you could actually reverse these stuff, and parent would be smaller than the right child node, depending on the sorting order. Okay, so what would happen here is you could actually have inserts like this. So usually we say that the write the right part of the subtree is larger than the parent root node. And left part of the left part of the subtree is less than the left node, or less than the parent root node is on parent root node. Sorry about that. Now, what are the complexities? If you would like to insert something in a binary search tree, insertion is order of log n. Deletion, oh man, delete is also order of log n. Now, search is order of log n. This is the best case. Worst case is going to be O of n. And I will show you in a minute why. Okay? So let's assume you would like to build a binary search tree. Okay? So insertion. Let's say I would like to insert something. So insert in BST. Now, what would you do? You say, okay, I will insert 8, for example. Now, 8 is actually like the data structure is empty. So here you go. First node, 8. You say insert 21. Okay, so because 21 is larger than 8, it will go right here. Okay. You insert 6. 6 is less than 8. It will go here. Okay. Then you say, okay, please insert 16, for example. Now 16 is larger than 8, it will go here. 21, 16 is still less than 21, so it will go here. Which is fine. Let's say insert 11. So 11 is still larger than 8. Okay. Less than 21, less than 16, so we put 11. Let's insert 5. 5 is less than 8, less than 6, so we put here 6. Sorry, 5, apologies. 5. Okay. Let's insert 5 again. Now here's the interesting part. This is a duplicate. Right? Now you could allow such a thing or not. For example, in this case, I will not allow. Okay, so I will say this is valid. And sorry, this is invalid. I will not allow it. So this here, throw error. So here, I could say error. There we go. Error. Now let's move on. Let's insert 34. 34 is larger than 8, larger than 21, so we insert 34. Okay. Then we would like, for example, to insert 3. So it's actually easy right now. So less, and then you go here, 3. Okay. You insert 26. Also easy. So you go here, it's larger than 8. 26 is actually larger than 21. So you go right. However, it's less than 34. You go left. 26. Okay. You would like to insert 7. I will not actually carry on anymore. You already get the idea. So we'd like to insert 7. So 8 is less, so 7 is less than 8, so we'll go here. However, it's larger than 6, it will go here. Okay? So this is how you would actually construct a BST. When you search for something, let's say you search for something, you search for, I don't know, 11. You will have this, because the height is log n in maximum. Okay? This is the height. You will actually have a hop literally by the height. So for example, you say, okay, 11 is larger than 8, so it will go here. However, it's less than 21, it will go here. However, it's less than 16, it will go here, it will immediately find it. Okay. If it doesn't find it, it returns null, and this is it. Okay. Now, the question comes here is like, okay, what happened with, what happens with in searching, well, like why we have O of n, right? So if this is log n and everything is fine, why would have this? You would have this if I tell you to insert in a sorted manner. So for example, here's a special case. Let's say you insert, I tell you insert 1. So you're okay, fine, this is 1. Then you would like to repeat the same process, insert 2. So because 1 is larger than 2, it will go here. Then I say 3. Then I say 4. See where this is going? 5. And so on, right? What you got is not the binary tree anymore, you got an array. Right now it's just a list. And if you would like to find something, you literally have to traverse this until the end. So right now it's actually not O of log n anymore. Right now it's O of n. And for that, we have a solution, right? So the solution for this problem is something which was called AVL. Another way to balance it, you balance it with something which is called red, black, ohm. Trees. Okay. And that's the pretty much the special case. Removal is the same thing as the searching, except you just simply like if you try to search, you like if I say remove something, you have to search for it and then you remove it, right? And I would like actually to stop recording right here.